Our next session is all about tools and practice. So we're going to get really practical now. And we've got a fantastic bunch of speakers covering tools from all types of practices, from the very small to the very large, everything from early stage tools specific to reuse and optimization. And I'm really looking forward to finding out more details about what our engineers are using. You can find all of our speakers' bios on our webpage as well. But during this session, we want to hear from you. We want to know what tools you have within your practices that contribute to retrofit and reuse, early stage design, and workflow optimization. So in the chat just now, you will find a link to a mural board, and we'd love it if you could share the name of your tool, what it does, and who owns it, so your business. I encourage you to think about this while you're hearing the presentations and add your sticky notes to our mural board. And this mural board will be open for a month. So if you can't think of anything now, you can come back to it later. So our first speaker of this session is Alison Wallace from SD Engineers, and she is going to share with us tools tailored for small projects. Over to you, Alison.
Thank you, Brogan. My name's Alison. I'm from SD Engineers. We are a practice of structural and civil engineers based in London. And I'm going to be talking through the domestic carbon toolkit, which we started developing about 2 years ago. We found we wanted to develop a way to communicate carbon studies on our domestic projects. We wanted a way to communicate sort of common optioneering studies that we were carrying out in the office to our clients. And also to do that, we needed a way to inform our team. So this study initially started out as an internal guide to knowledge share within our team, but has since developed into a guide that we can share with domestic clients and architects. One thing we found specifically with our domestic projects is that whilst no project is typical, there are lots of common elements and structural solutions that were common across the board. But each project didn't have the budget or the time to carry out a bespoke carbon optioneering study and calculation. So what we wanted to do was find a way to visually convey what we've learned and the tools that we can put into practice to inform projects at an early stage. I'm not going to go through all 36 pages. I'm just going to hit the highlights, but I will run through it so you can see the format of it. So we start off with a bit of a preface and an introduction, generally to inform non-technical clients about where the industry is. And we also introduced a couple slides about the route to net zero. Obviously, I'm not really going to touch on this here, but these slides were initially put together to actually knowledge share within the team, because we found that some members of the team were very up on sustainability and where the industry was going, but a lot of people, didn't necessarily have the same knowledge. So we wanted a way to share within the team where the industry is and where we as engineers sit within the goal towards net zero. And what this also does is helps inform our architects and clients, domestic clients, how we as engineers are engaging with the route to net zero. And we also talk about this embodied carbon hierarchy, because this is really key to reducing the embodied carbon on our projects. So we've split our guide into two key elements, the superstructure and the substructure. The superstructure, very specifically, we looked at the removal of the rear wall of a house, which provides the lateral and vertical stability, and the framing that we put in to support that wall, because that is an element that is very common to a lot of domestic extension projects. And we set the scene with the example and the study that we set up. So what we did is for each frame, we calculated the embodied carbon for each of the primary materials and the overall embodied carbon. And then for the benefit of the clients, we also talked about the advantages and disadvantages. So whilst a lot of the text is quite useful for the non-technical clients, the actual embodied carbon outputs are very informative for both our team and architects to be able to make a quick comparison of different studies. So we looked at the typical issue situation where you have a steel box frame, and we looked at the solution where you have it on a new concrete strip footing, but also where you are able to reuse the existing brick cordboard footing with minimal concrete. That's solution 1.1. What we wanted to do was compare that with a goalpost frame, which, in fact, not clear from the image here, would sit on pad foundations. As often, we quite often had the question of, well, is it less embodied carbon to have the extra steel member at the bottom, but the larger pad foundations at the bottom? The disadvantage in this frame being that it's actually less stiff as well. And I'll run through the comparison of these different options later in a sort of comparison graph. And then what we also wanted to do, because this becomes into the option of doing less, building less, demolishing less, is, well, what if we didn't completely remove the whole width of wall and we retained some masonry nibs that could provide the stability element and also reduce the depth of steel required? Obviously, the size of the steel and the size of the nib is very dependent on the loads on the frame and their desired width. And also whether you would willingly commit to retaining some masonry nibs very much depends on the ambitions of the project. We have in this study also allowed for underpinning the existing walls. But this provides a sort of quite a clear guide to an architect and client and our team of what the relative embodied carbon is. And then what we did for these initial studies is we provide a very handy little graph, which shows that actually a box frame on an existing cordboard footing is very similar embodied carbon to a goalpost frame on new pad footings and is actually much stiffer. So we would argue that this is a better option. And obviously less is less. And by omitting all the framing and with minimal foundations, you can make considerable savings in embodied carbon, but obviously compromising on the layout of your building. We then, as we started looking at these studies, we realized there were lots of different options and we couldn't really bring all the options into this study. And we looked at whether you'd had loft loading or not loft loading, or what you were extending your materials in, but we decided to try and just limit it to a few further refinements of some typical options that we usually include in our calculation model. The first one being pre-deflecting the box frame, which we sort of commonly recommend for all large openings. It helps us reduce the amount of steel by requiring the frame to be less stiff, by engaging the beam to take the dead load deflections before it's loaded. We also looked at introducing an internal column within the portal frame. Again, may not be desirable for a client's perspective, might be, but what this also does is provides a nice comparison of, as we all know, that if you reduce your grid, usually reducing your grid and having more columns can ultimately lead to a reduced carbon footprint. And we also looked at introducing an engineered timber beam into where we have just the single beam and not the frame. We did at one point explore the whole options of providing like a glue lam stability frame, but we just couldn't get it to work. The connections were just made it completely unfeasible. We've looked at engineered timber because of the shrinkage properties, obviously less than softwood, and also the required depth needed to carry the load. But there is a considerable additional depth to this option. And then we looked at reused steel and what we could do with deeper steel sections. And ultimately what we produced was a whole series of comparisons. I will very quickly run through to the bottom. We also looked at foundation options for single story extensions, because the nature of London clay and trees and the building regulations in London dictates that we quite often have deeper foundations than we need for a single story extension. and they really add to the embodied carbon of the structural scheme. So we looked at ways of minimizing concrete volumes and comparing different slab and foundation depths, which provide a very sort of neat comparison table that we can easily share with clients and within our team. And then we put some of these options together in an example project where we were very conservative on the gross internal area we used. We had a horrible schools rating, but we didn't really take the gross internal area of the existing building to be as conservative as possible. And then we played around with some of our options, replacing the strip foundations with beam and pier, putting in a timber joisted floor, low carbon block work, and what if we used reused steel, and we managed to improve the scores rating down to a D. And then you can actually also see where the reductions were in the different materials.
Brilliant. Thank you so much, Alison.
That's all. Thank you.
I'd now like to introduce our second speaker. We've got Jessica Foster from Civic Engineers presenting on reuse and retrofit projects.
Hi, as Brogan said, I'm Jess Foster. I'm an associate in Civic Engineers London studio, and I've been asked to talk about tools that we can use in retrofit and reuse projects. So as we all know, why we're here, conservation and energy and carbon is absolutely vital to keeping global emissions down, and a massive amount of the UK's carbon emissions are created by us in the construction industry. Now, the most efficient way of cutting carbon costs is use less stuff, and using less stuff for us is to stop building, but let's be realistic, that's not going to happen. But what we can do is take the buildings that already exist and reuse them, repurpose them, extend them, and make the embodied carbon that already exists earn its keep by doing more, introducing less additional material, energy, and carbon into the system. So this talk's really a brief introduction in how we can do that and approach these projects. If you've never done a retrofit project before, I'm hoping this will give a steer and signpost some key references and materials that will let you start. So how do we give new life to existing buildings? There's no rule. There's no rule I can offer. All buildings are different. They're different in size, in shape, in history, in condition. And what you're asking them to do is going to change massively as well. So everything you do has to be done with a lot of engineering judgment. But buildings are still buildings and gravity is still gravity. And the fact that the building's been around maybe longer than you have, it doesn't actually change the fact it's another engineering puzzle to solve. So there's no tool as such, but there are some great references and materials that will support those engineering decisions that you need to make. And the key one I'm going to talk about is this one, which is the iStruct Guide, Circular Economy and Reuse Guidance for Designers. In this, we aimed to pull together the thoughts and experiences of industry experts in building reuse, covering all aspects of projects, from making the business case for reuse, dealing with client expectations and risk, feasibility of reusing buildings, where to begin, analysis and justification of existing structures, design, and finally the construction phase and dealing with the involvement of the engineer on site, risks and temporary works. So I'm going to share a few of the key references and tools which we developed and are within this guide, and which I use and refer back to when I'm working on projects myself. So the most important part of making changes to a building, no matter what changes, is understanding the existing structure. This is the key to everything. You're trying to get an overview of the building as a whole, and generally the first step in developing this understanding is the desk study. Ideally, this will tell you what you might expect to find in the building, the likely construction type, age and history, and therefore its likely loadings, as well as the potential for maybe bomb damage or alterations and change of use. You've got to bear in mind that historic drawings are not as-built information, and it's typical for older buildings to have undergone multiple lives and fit outs, which can have structural impacts. So removal of columns, removal of load-bearing masonry walls, additional removal of windows, new floor openings to facilitate lifts, staircases, double height spaces. These are really, really common, and they will not be recorded on the original drawing. So it's really important to verify any historic information you have on site. So in addition to some guidance in the guide, The structural engineer has some really great guidance written by Fiona Cobb, which goes into their studies in detail. And the appraisal of existing structures is a key reference in understanding and interpreting an existing building and its condition. Now, you can physically see an existing building, you can strip it back, you can take measurements and work out load paths. So knowing the loads that the building was actually designed for is not so visible. You might get lucky and find a plaque which states the design loads, but this is the only one I've ever seen. So generally the answer to that is to go back to the original design codes. Now, design codes as we know them is a pretty recent phenomena, but since the 1920s, a large number of recommendations have been published, and these codes cover design with different materials and the live loads required for different building types and uses. We put together a timeline of design codes from the earliest guidance to the adoption of Eurocodes. And as you can see in the timeline, the later information doesn't necessarily supersede earlier guidance. So it may be necessary to consider multiple available valid codes and take a view based on the information available. Should also be worth noting that wind codes have similarly developed, but they've largely become more conservative. So it's important to consider the loads the structure was designed for originally, as well as the loads we'd apply for it now. You as the engineer need to bear in mind that, again, not all historic structures will have been designed and built in accordance to the codes or best practice of the time, especially later alterations. And it's necessary to judge the likelihood of this based on your other research, surveys and investigations. Now, these are really, really simple tools, historic codes, drawings, surveys, visual inspection, but they're critical to understanding the building you're about to alter and the basis of retrofit. And I should say you've got to understand the whole building, because an alteration that's happened 4 floors above you will impact the work that you're doing at the bottom of the building. So think more, use less. This is the mindset we adopt in retrofit designs. If you're adding stories onto an existing structure, you could just strengthen the columns for the additional loads being introduced. It would still offer a massive carbon saving over demolishing the building and building new. But by thinking more and making the existing structure fulfill its potential, we may be able to reduce our interventions even further. So if we're altering a structure, the only thing an individual structural element cares about is it taking more load than it was before? If you're adding stories to the top of a building, the beams aren't going to be impacted in any way. And by the same reckoning, if you're maintaining the load in a column by replacing something heavy with lots of something light, the impact on the column is actually 0, and that's what we call load balancing. So if a building was designed as a warehouse but is becoming residential, the live load the building was designed for was hugely higher than needed now, and that spare capacity can be used in other ways. So to add load onto a frame, we don't actually need to know the capacity of every member. We just need to justify that the member has sufficient capacity for the loads we're applying now. So this flowchart is a tool we developed and published in the Structural Engineer in this snappily titled article. We developed this when we were working on a retrofit project called Cannon Green, and used it to break down and communicate our developing knowledge and understanding of retrofit design. It gives a step-by-step guide to justifying additional load onto a building, starting with the simplest tools of load balancing. Is there sufficient capacity? Yes, fine, you don't need to do any more. No, you move on a step. Consider the 10% increase in strength from in a concrete structure. Does that give you sufficient capacity? And so on. And only at the very bottom of the flowchart do you need to break out columns to expose structure, to expose reinforcement, and actually analyze the individual member capacity. So this is that project. This is Cannon Green, before and after. It's in central London, 1960s building. And we added 2 additional floors of office space to the top, 2 new roof terraces, and the lower floors were retrofitted from car park to gym. And through that process of reviewing historic codes to see what loads would have been applied to the building at design stage, the minimum steel requirements for reinforcement quantities and connections, because there was steel in this building as well. We carried out detailed load analysis of the whole building and were able to justify the existing structure with almost no additional strengthening. Last couple of points, the guide also covers the circular economy and reuse of materials, both the practical and technical issues again, but also the challenges, legal and insurance considerations, how to design new buildings with the future in mind. And we're also very pleased in Civic Engineers to be on the steering group for the Engineers Reuse Collective. The Engineers Reuse Collective is a not-for-profit group of engineers who are working to promote the circular economy and urgently reduce the carbon intensity of construction. My colleague Harriet Browning is very active there and will be on the Q&A panel if anybody has any questions about this. Thanks very much.
Fabulous. Thank you so much, Jess. Yeah, we're looking forward to picking up some Q&A at the end, especially on the Engineers Reuse Collective. Thank you very much, Jess. And now we'll introduce the next speaker. We've got Alistair Thomas from Bureau Happold, who's going to present on early stage design tools. Over to you, Alistair.
Hello, everyone. Hopefully you can see my screen. So my name's Alistair Thomas, and I'm an associate at Bureau Happold. I started my career as a structural engineer, but actually now moved to head up our embodied carbon team within our sustainability discipline. And this might give my presentation a bit of added multidiscipline flavour. But following on from David's keynote speech, I will focus on his first action to do with early stage design tools. But before doing so, just a couple of notes. I think it's firstly worth saying that there's a vast number of tools out there, ranging from relatively simple spreadsheets to complex parametric models, all of which can be available to estimate and optioneer embodied carbon performance at an early design stage. I think in reality, the appropriate tool for you depends on several factors, including where you are as a business on your embodied carbon journey, maybe your computational prowess, maybe your practice size. So I would encourage the delegates to conduct your own research into the optimum tools that would suit your team. And hopefully the mural board that's been discussed and will be shared as part of this session will provide some further guidance on this. Secondly, fully back the iStruct approach in that we are to achieve the carbon shift and performance required in order to meet sector targets. We need to work collaboratively as an industry. There's lots of great free guidance on the iStruct resources page, which has been co-created with experts from across the industry. So based on this, I'll focus on free tools that are partnerships with the institution or have been identified resources with other organisations, and then share some tools that we're using as a business, which we have created for our internal needs to illustrate our journey. So firstly, and hopefully this is a reminder for many, but there's the iStruct structural carbon tool, which was first launched in March 2021. And it's an Excel-based tool in partnership with Elliott Wood, and it is completely free to use. The tool is based on the iStruct How to Calculate Embodied Carbon Guide, and it's regularly updated, most recently to align with the RICS Whole Life Carbon assessments for the built environment second edition. This means that you can be assured that it's aligned with latest industry best practice and can be applicable worldwide. The tool allows for quantitative decision-making relating to embodied carbon with the aim to reduce emissions. You can assess 6 different schemes within one workbook, and the embodied carbon narrative is aided through automatic graphic creation as well. And the results are granular, so the tool can be used to identify carbon hotspots and therefore opportunities for improvement. It's worth noting, like with all early stage design tools, there is definitely a degree of uncertainty, and the aim is not to provide highly accurate assessments, but a straightforward means of comparing different possible design solutions. So there are other tools available that look to automate this process even further by generating the different possible solutions based on certain design criteria to allow for the material quantities to be estimated automatically. And there are some excellent products available out there, although they do often tend to come with a cost associated with them. So within Bureau Happold, we've developed our own tool which specifically meets the required needs we were regularly finding on our own project, focusing on possibly those more standard items so we can focus on the areas that maybe require more lateral or in-depth thinking. This tool is based off open source code via the BOM, which I'll discuss in greater detail on a forthcoming slide. But it enables fast-paced option comparisons of different floor configurations, which can take place in live workshops with the rest of the design team and has led to some really successful results. And the tool also produced some of the results that are in the embodied carbon structural sensitivity study, which is available within those iStruct resources. So changing tack slightly, in my current role, I've seen how easy it is for individual disciplines to strive to improve their performance, focusing on reducing the carbon impact of their own elements of the design, but losing sight of the impact that might have on other disciplines and the project as a whole. For example, does rationalising the grid spacing require the facade panelisation to become more complicated, potentially increasing carbon emissions? Does a specific framing solution preclude the optimum solution for the services distribution, requiring increased floor-to-floor height requirements? And in addition, it shouldn't be forgotten that embodied carbon is not the only environmental or even design metric that needs to be considered, and therefore we need to avoid this carbon tunnel vision. Therefore, whilst it's essential it's considered, the embodied carbon of the structure should be compared as part of a wider design decision-making metrics. And this tool can be as simple as a RAG rating matrix, but it's imperative to ensure that holistic process is engaged with. Let's say from a structural engineer's perspective, you should be cognizant of this and engage with this process with the team and make sure any design solutions you're suggesting align with those other disciplines. So within Bureau Happold, we've aimed to take this a step further, developing an innovative framework within which a whole building can be modelled and the value of its parts evaluated simultaneously with a game engine interface, which you can see running on the right-hand side. And this is part of a discussion that we've had previously about engaging clients on this journey. So in this instance, we're looking at an existing building and the potential different options available for it. So the idea of the tool is to discuss and agree the importance weightings of various factors, rapidly assess those design opportunities, combine those into prototypes, and then present those prototypes with the scored results. And it enables a design process to be set up in a way that lets clients, stakeholders, and the end users actively engage in the process. And this is where we see the future of early stage design heading. So what's its relevance to this conference? Well, this is developed within the BOM, which is the Buildings and Habitats Object Model, which is a collaborative computational development project for the built environment. And it aims to standardize the data and functionality that architecture, engineering, and construction domain experts use across all disciplines. And so the LCA toolkit, which sits within the BOM and is used to develop this rapid prototyping approach, is free and easy to use and can enable the quick comparison of potential multi-disc solutions because it pulls from the many different softwares simultaneously, and therefore you can have that holistic thinking. So as Jessica has previously alluded to, promoting the circular economy is going to be a key driver in reducing carbon emissions going forwards. And the previous tools can enable the embodied carbon impact of retrofit projects to be compared and estimated against a potential new build, so that when combined with other factors, an optimum solution for existing buildings can be achieved. But for those scenarios where we get to a stage where we're looking to use existing buildings as material banks, there are tools available and lots of developing research to facilitate the use of reclaimed material. This is probably most predominant with steel due to the relative ease of disassembly and its viability for reuse. And you've got tools such as the HTS stock matcher, which is freely available and allows design steel to be compared against steel stock lists to identify where elements may be substituted most efficiently. I think in a market where steel reuse suppliers have recently closed that part of the business, your steel reuse has an even greater chance of success in situations where both the new building and donor site are directly under the influence of the team. You can see an example here on the right-hand side where you can apply those same principles to use as much of the existing steelwork as possible in the new. And going forwards, there are also a greater number of projects looking at the reuse of, say, concrete through PREX, which is the piecewise reuse of extracted concrete in new structures. And for concrete, the extraction is not governed by the elemental pieces themselves, but one is also defining the size of the pieces based on program, lifting time, the exact form of the concrete that is being used there. And scripts can help to rationalize the cutting of the existing concrete based on these parameters to meet the needs of the new use. And that's something we're looking at currently and hope to share in the near future. It's worth also highlighting that the iStruct has a circular partnerships database, which is regularly reviewed and has a list of vendors who responsibly source building materials. Here, I might be very slightly extending the brief with regards to early stage tools, but I think that ensuring the good design practice is realised in construction is critical. We've seen many projects over the years with really aspirational sustainability credentials fall down and be exposed to carbon creep through construction, essentially because there's been that breakdown in communications and the expectations of the contractor. So firstly, we'd urge transparency as part of this process, make sure everything is shared fully, design decisions, assumptions that have led to the embodied carbon results at pre-construction. And with regards to a tool, specification is a key tool, and we advise that you've got clear guidance on the carbon requirements of key materials, preferably aligning those with carbon performance to give the contractor the scope to achieve the targets, but adding appropriate caveats where necessary, of course. And then as a final slide, perhaps the most important early stage design tool is monitoring the actual performance of our buildings. This is the true metric of the success of any interventions and reduction measures that we're proposing. So within Bureau Happold, we've set up a dashboard which monitors the embodied carbon of all our projects and captures some key details so we can start to build trends in the data. I know many other practices are doing the same, and Ramboll have shared theirs through their compare tool. So those are publicly available to look at their data. But it's also equally important that data is submitted to platforms that have been set up for the wider industry. So you've got the Built Environment Carbon Database for the UK, which is free to access and designed to become the main source of carbon estimating and benchmarking for the industry. It will become a practical instrument to support decarbonisation of the built environment. And also, finally, it will improve the confidence in whole life cycle assessment data, which will be a significant step in moving forward and improving policy for embodied carbon, providing that additional lever for us to achieve greater reductions on a more significant majority of our projects. Thank you.
Fabulous. Thank you so much, Alistair. Just a reminder to our audience that you can put some questions in the chat from any of our speakers so far. And we will move on to our final speaker for this session. We have Tristram Carfrae from Arup, who's going to be presenting on material efficiency and workflow optimization. Over to you.
Thank you, and a good day or a happy evening for me to everybody listening to this or watching this. So I'm going to talk a little bit about material efficiency and workflow optimization, but I'm going to start with remembering that this is all part of a whole framework that I think everybody's been addressing already so far. So we've got, the best thing we can do is to reuse and adapt existing buildings. The second best thing is to keep existing materials in use using a circular economy. The one I'm talking about is improving material efficiency and potentially reducing the weight of new construction using lower carbon materials. I'm a big fan of using modern methods of construction to make construction more effective and reduce waste. And also the whole thing is based on whole life carbon assessment and being carbon literate. So what do I mean by that? I've cheated here with this slide because I've taken scores, which is meant to relate to the whole structure of a building and only relating it to the floor system itself. So I'm ignoring columns, lateral structure, and also foundations and substructure. But here you see sort of typical business as usual today of what you might see in the commercial market of post-tension flat slabs, steel with CLT infills, or steel concrete composite structures. But the point is that we all need to have an understanding of what is usual and what is possible. Because my view of when you come to a new build is you should start by actually deciding what your objective is. What is your carbon budget for your project? And then how will you get to that carbon budget? And I've put some measures down here which I would approach. One is a sensible grid. And a sensible grid to me is about 9 meters by 9 meters, unless you're using timber, in which case it should be a bit less. You should minimize basements. They're pretty carbon hungry. Get rid of transfer structures. Direct load paths are the key to making something materially efficient. If you're going to have cantilevers, make sure they're balanced on the backspan, so about 3 meters for a 9 meter grid. Very important to me is to optimize all elements for their actual forces. Traditionally, we would sort of size the biggest beam or the worst loaded beam and then run it out on a whole bay. But actually, it's much more efficient and weight and carbon efficient to size every element for its actual job. Last one is to carefully manage your design contingency, which I'll talk a bit more about later, and then establish a digital workflow that allows those things, particularly optimization and the management of your design contingency, to actually happen. So the digital workflow I'm using to illustrate this today is very simple. We have more sophisticated digital workflows in Arup, but I'm sticking to the sort of tried and tested here, the commonplace, which starts with a direct input of geometry using, for example, Rhino and Grasshopper, in our case, into a structural analysis tool, in our case, Oasis GSA, but it doesn't matter which analysis tool you're using. I then advocate the ability for automatic element sizing, just so you can get a quick handle on the amount of carbon. So this is for the more bespoke projects. So it's in partnership, if you like, for what you just heard from Alistair, which is sort of standard configurations. I'm saying on a more bespoke project, you want to be able to very quickly evaluate the amount of material used and therefore the amount of carbon in any particular approach to design. In my case, I'm using the GSA design layer to do that. You then want to be able to move that analysis information into the communicated information via a BIM model. In our case, we would use Revit for most models, and we get from GSA to Revit via Rhino and Grasshopper using the Rhino Grasshopper inside Revit tool. And then lastly, which I'm not going to address further, but we use coordinate between our Revit models, the architects, the other engineers, etc., using Revisto, which is a three-dimensional viewing tool, if you like, to compare the information coming from different sources. So automatic member sizing, this is an example of a roof I'm looking at the moment. It's a way of exploring the solution space, so you can try different things. If you can quickly evaluate how efficient or inefficient they are based on your carbon budget or weight budget that you set initially, and then you can learn from each iteration and try something else and try something else and try something else. And I would expect to get through about 4 models a day, getting through about 20 models a week, as in 20 different ideas to assess which is likely to be the most productive. As I said earlier, I believe we should optimize each element. If later in the project we decide to rationalize some of them, all well and good, but you should know what the minimum weight is and the minimum material consumption possible before you decide to spend more material and more carbon on making it rational. I build contingency into my load factor, so you can see perhaps poorly on that slide that at scheme design I would have a 20% extra factor on all my ultimate load factors, which you then gradually reduce to nothing when you do the final construction information. And this is a way of explicitly and linearly managing design contingency, whereas if you change the utilization factor at different stages, it's a non-linear formula, and you can get very lost in what's actually going on and also fail to release it later in the project. The next step is direct model creation. So this is getting directly from the analysis model in which you've automatically sized everything into the building information model from which you're going to produce your documents. As I said earlier, we go from GSA to Revit via Grasshopper / Rhino inside Revit. And we use the Grasshopper scripts to actually add all the additional information required in the model to help with the documentation, like, for example, member tags, things like that. Anything that you need to add to the model gets added at this stage, but in a repeatable process, because what you want to be able to do at every stage of the project is to resize everything, for example, reducing the design contingency, and then automatically reload up the BIM model with that information. And then inside Revit, of course, you then set up the actual documentation. Unfortunately, it still seems we're stuck, at least in my experience, in a largely still a two-dimensional documentation phase where everybody insists on having, pseudo paper, as in PDFs, of the final information. So Revit is the best, in our view, one of the best ways to set that all up. So again, once you reload the model, you can reproduce all the documents as well. There are some problems in this idea of trying to get a repeatable process. For example, if you're going through to actually document steelwork connections, for which you might use Tekla from Trimble, it's harder to make that a repeatable process. So you've got to sort of hold off doing that until you've got your final documents, or at least know what you're doing and do typical ones, but only do the full set of information almost at the last possible minute. And the same applies if you're going to document your concrete reinforcement in 3 dimensions. It's something that's very hard to make a repeatable process in our experience. So finally, I'm just going to show you a few projects where I think we're pushing the boundaries of what's possible in terms of new slabs. These all relate to a commercial building on a 9 by 9 meter grid. This vault that we built a prototype of with Laing O'Rourke uses an average of 150 millimeters of concrete using 100 mil square slabs. The 100 millimeters is actually chosen to give you a 90-minute fire rating, which is about as low as we normally can get on a commercial building. This comes through at 45 kgs of CO2e, so that's A++ on my cheating scores rating. It's got 11 pieces of prefab to be lifted into each bay, but we're using quite a lot of structural depth to get the structural efficiency, although you can interweave it with the services both above and below the structure in the same zone. From that, we developed our thinking further to do this much simpler scheme, which is using a bit more concrete. It's not quite as efficient. Same fire rating, a little bit more CO2e, up to 50, but it only uses 5 pieces per day with no complex connections and is in 250 millimeters of structural depth rather than 900. In this case, you just run the services in a separate zone below it. Now, the cheating bit is to introduce these column heads, because it doesn't actually matter if you occupy with structure some of the occupiable space, because there isn't actually anything in that bit above 2.1 meters and below, say, 2.7 or 3 meters, where a ceiling might be. You can put some structure in there, provided it's beautiful and occasional. Another more radical idea is to use a lower carbon material, in this case stone. So we've learned from our work at Sagrada Familia that we can actually do whole buildings using post-tension stone panels, in this case double T units and primary beams, and that would get us down to sort of 25 kilograms CO2e per square meter, and still on the idea of 4 pieces per bay, per 9 by 9 meter bay, but using a bit more structural depth, maybe 500 millimeters. That could be shaved a bit depending on the strength of the stone you've got available. And then lastly, going back, this is to the circular economy. This project is was hot in the press in the UK. It's a redevelopment of the Marks and Spencer store on Oxford Street, which is existing is 4 sort of miscellaneous assortment of 4 different buildings built in different times using different structural systems. It's woefully inefficient operationally as a retail building or collection of retail buildings, but also its operational energy efficiency is appalling. And we've come up with a scheme which got planning permission last year, thanks to my colleague Kerry Greaves, of reusing all the existing material from the 4 existing buildings to build the lowest buildings, and then putting 3 more stories on top using the vault system I showed you before. Now, the technique here is not to design what you want from a clean sheet of paper, but instead to start with what do you have available in terms of materials, and then designing a structural system that reuses those materials that you have available. So in this case, the bottom stories are this jack arch system using the steelwork available from 2 of the buildings with bits of cut up concrete to form vaults. And above that is a concrete only and tie rod system for the next few floors, the revault bottom left, and then finally the new vaults at the very top. And again, this system is coming in at 25 kilos of carbon per square meter for the complete, cutting up, reprocessing, and putting back together the existing material. So thank you very much.
Thank you very much, Tristan. I would like to invite Jess, Alison, and Harriet as well, if you're online, to turn your cameras back on, and we will have a bit of Q&A. So a reminder to our audience, please ask your questions in our Q&A tab. I thought I'd just start off, Tristan, I found that was a really great presentation. Thank you. I really liked your pragmatic, actionable list of like low carbon for new builds. And you shared some great project examples. Lots of things on computational tools and design. If someone was new to computational design methods and optimization, might be overwhelmed by the concept of grasshopper, where should they start?
Well, I think the starting bit is exploring the possible solution space. And it doesn't matter if you can't automatically size everything, just use a nominal stress level in steel or stress level in concrete as your target, and just see how, experiment with what different structures, will use less material and achieve those target stresses. It's about exploration and trying to find different ways of doing things that are more efficient. For me, the tools are less important than the attitude.
Mm. Yeah. And is there anywhere for people who are maybe in smaller practices, is there anywhere they can go to get guidance or training on using computational tools?
I'm probably the wrong person to ask for that question, unfortunately, Brogan. I'm sure the iStruct is full of resources, and I'm sure our colleague Will would help anybody, that asks to find the right resources to do what they want.
Yeah, we will. I'm sure we've got a lot of them on our big spider diagram. Thank you, Tristan. I'm going to move over to Alison. Thank you for sharing your tools and your report that you've produced for your clients. How successful have you been to integrate those lessons, and have you faced any hurdles during your path?
Yeah, mixed, I'd say. I definitely think that we have specified some beam and pier foundations, and actually they've just been put in as really deep trench foundations and filled with concrete, because the ambitions of the project probably weren't sort of communicated or really sort of taken on board by the contractor. I would say the main thing is how engaged is your client in wanting to save carbon, bearing in mind that in the grand context of things, their project is, quite small. But then also how engaged is your contractor? We've definitely specified using reused steel, and then the contractor has just gone ahead and procured virgin steel with their preferred steel subcontractor. But then we've learned from that, and then on the next one, we were very involved in the steel procurement process and sort of essentially did a lot of the role of the steel fabricator because we knew the hurdles that we'd face. But yeah, I think where we've had really engaged clients who want to save on carbon, we've argued for reusing existing structure at the compromise to the structure. But generally, nobody wants columns and everyone wants a big, lovely open kitchen. But they're not really fussed what you do with the foundation. So then it's a question of being on site and communicating with the contractor as to why you've chosen a particular foundation solution and making sure it's viable. I mean, digging really deep piers aren't actually that straightforward. Is it a viable option? So yeah, definitely had ambitions which haven't been realized on site. So that communication with the contractor is key.
Absolutely. Thank you for that. I've got a question now for Jess. In retrofitting the Canning Greens towers, how is the roof extension prioritised in the design process, given the limited redundancy and potentially constrained reserve capacity of the RC frame, particularly for material choices and structural configuration?
So one aspect is we did try and keep the roofs as light as possible. They were structural steel, but they did have concrete decks because that's what's practical for this kind of building. What we did do though, within the load balancing exercise, we actually offset the structure of the two additional floors. So the first floor of structure loaded certain columns, and the floor above it was actually offset to load the alternate columns. So the load was spread around the entire building and distributed much more evenly. So we played with our layouts to force the load to distribute in a way that didn't overload the columns. I think. Did that answer it? I'm not sure, but yeah.
Thanks, Jen. We've got a question for Tristan from Bethany. She says, love the vault designs. I agree. I think the vaults are really beautiful. I'm all for vaults coming back. Do you think there's scope to reduce carbon even further by researching 3D printed concrete and additive manufacturing? As arches and domes work in compression, therefore we're negating the requirement for reinforcement. And maybe to add to that as well, Tristan, if you may, could we talk about like the practical constructability of domes and arches too?
Yes. Well, I could talk a long time on this, Brogan, so I'll try and be brief. The advantage of working things in compression, and by the way, to work things in compression, you have to understand friction, because that's the way the compression joints work. They can't take tension. So it's quite a big leap for the average engineer to start trusting friction as their primary load path. Yeah. So it's not for the faint-hearted, but it'd be the first thing I'd say. Secondly, what you use in compression can be anything. It can be chopped up bits of existing reinforced concrete. You're not going to rely on a reinforcement necessarily, just the compression strength. It can, as I said, be stone. There isn't, in my view, that much advantage in 3D printing because of things like fire rating. As I said, to get a 90-minute fire rating, you need about 100 millimeters of concrete. To get a 120-minute fire rating, you need 120 millimeters of concrete. You can print things down to 40 millimeters, but that won't save the day unless you use something else to get the fire rating, maybe layers of gypsum, and then you've got to add those back into the calculation, if you see what I mean. So I think 3D printing is very, very interesting, and in the right situation where you really want lightness and don't necessarily need compartmentation, it's absolutely brilliant, but it's not a universal panacea. And as you say, constructing domes is normally needs centering of some kind, not continuous false work, but centering. And it's why the vault I showed you actually uses only 9 panels, is to try and minimize the amount of temporary works required to do that. So you can drop in. Even then, we found that lifting 3 by 3 by 100 millimeters bit of concrete is actually beyond the standard precast lifting element, because it doesn't properly anchor in only 100 millimeters of concrete. So you come across all sorts of little things, a bit like Alison was just describing, that get in the way of the best intentions.
So do you think there's a future for domes and arches in traditional buildings that we are designing today?
Absolutely, but again, it's not a universal answer, I don't think. It's an interesting answer. It has its place. I think the use of it on the M&S Marks and Spencer proposition, where large volumes for retail are appropriate and in fact desirable, it all sort of makes sense. It wouldn't make much sense in a speculative commercial building where trying to get the right number of stories into the available height
Yeah.
is a dominant thing. So, it's horses for all these things. Nothing is universal in my view. Every project is special, and every project needs to be considered in its own context, environment, ambitions. But the trick is to do the best for that project.
Absolutely. Yeah, I can agree more. Thank you for that. And I want to ask a question to Harriet. Harriet, thanks so much for joining us. Harriet is an associate at Civic Engineers and is going to tell us more about the Engineers Reuse Collective. So for anyone who's on the call who are maybe not familiar with the Reuse Collective, how can they get involved and what are you guys up to?
Hi everyone. So yeah, I sit on the steel reuse working group of the Engineers Reuse Collective, but at Civic we're part of the steering group as well. It was set up at the start of this year, and we've actually already had lots of events, some of which are free to join for non-members, so I'll say more about that in a moment. But it is started as a collective of groups of engineers who were already trying to promote reuse and get reuse going, and all coming up against the same hurdles. It's a pretty universal problem across the industry. So rather than us all tackling it individually, the idea is that we will tackle it as a group. We'll take best practice and the knowledge learned from various reuse projects across all the practices in the collective and come up with standards, simpler ways of doing things, and also improving communication with other parts of the industry. So the group is made up of structural engineers, but we're working with demolition contractors, main contractors, other designers to make reuse simpler and make it the norm. So rather than it being a completely innovative idea, which tends to fall down at the point that a contractor is involved because it is more risky at this point, we're trying to make that easier and make it the default position for projects. So it's there's lots of different strands, but the key strands to the collective are sharing best practice and crucially sharing what's gone wrong. So we have events which are closed sessions, not recorded, that give people the opportunity to say, in a commercially sensitive way, if they need to, how they've attempted reuse and where it's gone wrong, and what we can learn for other projects, and also sharing where it's gone really well at various design stages. We've had in-person events where we share specifics of, for example, reusing foundations, reusing steel. And separate to those events, we have working groups which are developing standard documents. So I, for example, am working on developing specifications for steel reuse, which would then be industry-wide available. Anyone can get involved either from a company perspective or as an individual. The prices, etc., vary depending on the size of your company. There's lots of engineers already involved. I think there's about 50 practices within the collective. Always looking for more. So feel free to drop me an email and I'll put into the Q&A. I will add in a link to the Engineers Reuse Collective now.
Fabulous, thank you so much. That was an excellent summary. And I've got a question for Jess from Alfred. Given legacy load limits like 2.5 kilonewtons per metre squared seen in older London RC frames, how should retrofit designers balance the need for intensified modern use with the realities of the inherited structural capacity? And when does strengthening become less sustainable than the spatial compromise?
Well, I mean, 2.5 is a pretty generous load allowance. I mean, I think we need to be challenging some of the assumptions on what's needed in buildings. So there's no, as I said before, there is no sort of one-stop answer. If we think a building's been designed for 2.5, it's quite easy to justify columns. It's harder to justify slabs, but it is possible. But I think challenging the assumptions that actually an office needs a certain load allowance when in reality it's 6 people sitting with laptops becomes part of the bigger conversation, really.
I guess following that, you're right. Like, we need to challenge what our buildings are doing. You know, have you had any conversation with your clients before to challenge, you know, their use scenarios? I know, you know, in the circular economy and reuse guidance, there was a section saying, you know, to reduce the overall live load, you actually maybe could set limits in, you know, in spaces to how many people could be, you know, utilizing it. Have you had any examples where that's been effective?
Yeah, I mean, back to Cannon Green in the basement. So the tower, the slabs were fine as they were, the beams were fine as they were. We weren't changing the use. In the basement, we were going from car park to gymnasium, and actually gyms have a really high live load because people are picking up heavy things and dropping them on the floor and jumping around and doing all sorts of things, which seems counterintuitive compared to cars, but that's how it is. So we did a lot of exploration. We actually had to sort of justify the slabs and the beams down there. But in some areas, we had the choice of either strengthening the slab or saying, you know what, this area, can you put your reception here? Like, this area is not going to work as a gym without being strengthened. How about, you know, architect, how about we actually define this area as reception space and, you know, limit the load that you're going to put on this space so we don't have to strengthen it. And so that was, yeah, built into the design of the gymnasium. This area was changing, this area was reception, and we really only focused on the floor areas where we couldn't bring the live loads down to suit.
Great, thank you very much for that. I've got a question for Tristan. As the structural engineering community responds to the climate emergency, what role do you see for AI-driven optimization in delivering truly low-carbon designs? And are there any examples where AI has already been embedded in available tools or workflows?
And we have examples of where we've used AI on projects, but not, I think, embedded in existing tools, available tools and workflows. In other words, we've been using machine learning for some time as a sort of core, particularly as it happens in assessing existing buildings. So one technique we've developed is where you don't know what the construction of an existing building is, you make a lot of reasonable guesses and assumptions. You analyze those, and then you use a sort of probabilistic approach to say what is it likely to be capable of, or for future use. And we've used machine learning to help drive that because it's a computationally very intensive thing. We've done similar things where we've looked at buildings threatened by earthquakes that weren't expected to see earthquakes. Are they likely to survive or not? And where the most vulnerable? And again, without doing lots of assessment, we just used pictures and photo satellite imagery and then assumptions about what the buildings are likely to be and how they're likely to be constructed, followed by massive amounts of analysis and machine learning to assess where the weakest buildings are likely to be that could do with seismic retrofit. So we have done these things, but I don't know of anything that's readily available right now, but it will come, right? So I'm going to say something on a side note, if you like, and it comes from actually from Alistair's presentation, is we at Arup have developed a lot of tools over time to help us on this, reducing carbon journey. But actually, it's pointless every consultant having their own tools, really. What we need are industry-wide tools and us all coming together, just like we've heard for the initiative that Harriet presented, to share information. And again, the carbon data, we've got our own carbon, data store of all our projects, but it's much more valuable to have that in public in a common place. So sometimes, this is a bit weird, sometimes it's better to wait for the whole industry to move forward with software that's readily available to everybody than it is to get too excited and develop all load of stuff for yourself. You see what I mean? So don't think you're missing out if you haven't got the right tool available to you, because it will come. And when it becomes as a mass market tool, that's when it will be most effective.
Completely agree. And we can see in the Miro board that there's some open source tools that have been shared and suggested. We have a couple of organizations' own internal tools. And I'm sure you'd find, we've got some tools in Rambo, you've got some tools in Arup. I bet you put all those time together, we've been highly inefficient across the industry at doing the same thing. So I completely agree.
Completely.
And we can all take a leaf out of shading. It's a very altruistic mindset, and I appreciate that maybe not all businesses would want to share an open source, but there is, there's a greater good here that by sharing our tools that we can help and support others and businesses that might not be able to fund creating tools, because it is also quite an expense. So
Yeah.
Completely agree. Thank you for that. We've got a few questions coming in on materials. So this is a question to all our panelists here. If we've got any experience with using LC3, which is calcined clays, or carbon fiber reinforcement on your projects, and do we see future in these types of material innovations, and interest especially about whether carbon fiber can be used in vaulted structures as well.
So I'll jump in first. I think yes, we see a lot of opportunity in calcined clays and other Portland cement alternatives. Yeah, which one again? You've got to look at whether it's readily available, can it be mass produced, etc. So, but calcined clay seems to be one of the favorites at the moment. First point. Second point, the vault I actually showed you, the prototype built by Lang O'Rourke, we used basalt reinforcement. Basalt, which was very interesting, and also used sem-free as a cement substitute. So that the actual product that I showed you there came down to 25 kilos of carbon per square meter with using those two, as well as efficient construction. So again, all this is happening. I'm personally frustrated that green steel isn't becoming readily available more quickly. It's a known and understood process, as I understand it, from the direct hydrogen reduction of iron through to electric arc furnace steel production, but there's just not enough capital investment going on in the steel industry to get there. So you never know whether you should specify a material that will become, less carbon in the future on the basis that you want to encourage more people to be producing it in the best possible way, or whether you should temporarily sort of shun the material until the right material turns up. But in the end, you have to work with the supply chains available. Otherwise, you're tinkering at the edges as opposed to dealing with the bulk problem, which is ultimately we still have to build as much building as currently exists between now and 2060. So that's a sobering thought. However much reuse and adaptation we do of the existing, there is still a continuing global demand for more floor space.
Thanks for that. Thank you, Tristan. Any other panelists? Do you have experience with calcium clay, fibre, basalt, or perhaps any other material innovation, bio-based, that we've maybe not talked about?
At Civic, we're exploring a couple of projects using calcined clay in concrete. I would say it is still very tricky for us. It's seen as a high risk item. I think it really depends on the client and the contractor as well. I feel like we need, with these innovative options, to pick our battles and focus our efforts on the clients that we know really invested and engaged in this, and then we build up that precedent to apply more widely. That seems to be working as the best strategy for us in terms of investing our time in pushing these materials forwards. But we've also, in the process of looking at that, at calcined clay in more detail, we actually have changed how we specify in our MBS specs now. So we specify based on the carbon budget of the project, and we make it clear to clients and to main contractors that we will be working much more closely with them and with their subcontractors, because they're the experts in specifying, particularly because there are so many options emerging within concrete.
Mm-hmm.
So rather than us potentially closing off opportunities, especially for very large projects which might not be built for another couple of years or even longer in some cases, we work on a carbon budget and then just work really closely with those concrete subcontractors to get to the best solution. And actually that's been so valuable for us because, as I said, they're the experts and they can teach us a lot.
Yeah, absolutely. Yeah, that approach is been widely adopted by others in industry through Concrete Zero, moving towards, like say, a performance specification, which is within our control as engineers, and then the carbon limit, whether that is through a total carbon budget for the project or using the low carbon concrete group or the universal classification system. For concrete, there's various ways and methodologies. So much so, the government has now put out a consultation asking for everyone's opinions on which type of methodology we should all use now to look at steel and concrete. So yeah, it's still a minefield, but it's a really positive approach.